Let's show the picture. Okay. The structure here, as you can see, the structure here. This is the structure, right? This is all fundamental frequency that's here. And once I input the, okay, 1 Hz, for example, of force, right? Force, 1/4 of the fundamental frequency, what happened? Frequency become 1/4, right? This is 1/4. 1/4就表达时间只剩下4倍。Okay, once you frequency divide by 4, you okay. So your amplitude like this. Okay, it's a 1/4, not amplitude. Your amplitude like this, one wave, right? One wave in the 1/4. So you kind of move this particle, move this vortex above here, move this vortex here, move this vortex here, move this vortex here, and eventually these four vortex merge together. Okay, because once you move the vortex here, move the vortex here, and this vortex will be merged together to become one. We call the vortex merging. So she find out the one mechanism for the vertex merging by input the subharmonic frequency. The regular is you can put a 1 of 9 to have 9 vortex merged together into one. That's a potential. So once you merge, what happens? Mixing is enhanced a lot, very short time. Okay. So that, as you can see, our original mixing length is flowing with this. When you have a nice, you will going like this. Okay. You have a huge vortex. Okay. And now we shorten our what? Our combustion chamber. The problem with the combustion chamber is what? Flow is moving very fast, right, in the combustion chamber, even when we slow it down already. Right? And then once this moving, combustion need to take time, okay, to mixing. So you need the combustion chambers such a long, okay, for them to mix and then ignition and combustion to take place. Right? So combustion chamber needs certain length. If you can shorten this mixing length, you can have shorten your combustion chamber. Okay, that's one kind of application for this. Okay, I think that will be the additional story. Okay, in the 1980, okay, something like that. Okay, recently I think some research still doing that, but not as popular, but still the concept is still going. Try to use in the flow control. As you can see, a lot of paper is still doing that. Okay, finally, we call this has a velocity difference. We call this kind of instability is called the Helmholtz instability or radial instability. Okay, this is once you have velocity shear and general instability, we call this is Helmholtz or radial instability. Last case. Case what? Case 4. Case 4. Okay. So what is case 4? Case 4 give you what? U1 equal to U2 equal to 0. That means we don't have any velocity at all. However, low 2, low 1. Okay, we have a different density, but there is no velocity. Whatever. Again, we go back to our this. Mess up. I need alcohol. Anyway, I think I can read them here. Okay. U1, U2 equal to 0. That means this term is vanished, right? This term. Okay, so this term is vanished. Right? Low 1, low 2 is different. U1, U2 equal to 0. So last term also vanished. So our sigma is equal to what? Right? Okay. So this is our sigma. Okay. This is our sigma. As you can see here, sigma is a positive negative square root of this. So inside this square root here, okay, depend on your low 1 and low 2, right? Could be imaginary, could be real number. Okay? Let's discuss a little bit. When low 2 greater than low 1 have what happened? Low 2 is greater than low 1. This become negatives. And negative mean what? Negative mean you have the imaginary part, right? Sigma I happen. And sigma I happen here. And sigma I is equal to, is greater than 0, right? Since the low 1, low 2. So what's the low 1, low 2? When low 2 is greater than low 1, low 2 is greater than low 1, what happens? This is heavier. This is heavy. This is light. So we have a heavier fluid, density high at the top. And then we have a density, lighter density, medium below. And this is unstable. Okay, this is unstable. Vice versa. If your low 1 is greater than low 2, what happens? Your low 1 greater than low 2. This is heavier fluid. This is light fluid. Stable. Okay? So that will be conclude, okay, our final case. This kind of instability you call this Taylor instability. Okay, Taylor instability. And the case for the Taylor instability can be seen from here. This is a mixing layer we show you already. Okay, and then here is another case, is shear layer equal to flow over a cylinder, right? When flow over a cylinder. And then once you have a small perturbation, and they start to glowing and glowing. Okay, so we have a so-called vortex shading, but behind the flow cylinder. This is also the one of the unsteady problem. Okay, and finally here we have this field, flow field. Okay, we have to wait a little bit. Okay. Okay, no, let me see. Okay, I think I have to waiting for that. This is already in Taylor instability. Heavier is, okay, once you small perturbation interface, the light fluid will be going up. The heavier fluid will be light going down. Because you generate small perturbation and the interface is unsteady. At the beginning, if it's steady, they can keep, but it's very unstable. And once you perturb, the heavier fluid always is flowing down, right? Because the density is higher. Okay, I will generate like this. So that will be called Taylor instability. This is Helmholtz instability. Sometimes we call it Helmholtz instability for mixing layer. And Rayleigh-Taylor instability, we call this. This is density different. Okay. Okay, so that will be the conclude our lecture for this semester. Okay, this is final. So that, okay, I think, and if you want to study there are two books actually. Okay, so this is one. Okay, this is one of the textbook for the hydrodynamic instability. Okay, this is a very old book. Okay. Yeah. And then in this book, okay, let me see. It gives you another okay, this is all similar. Okay. Mathematically, you may be afraid. Okay, but anyway. Anyway, and I would like to show you the last thing I have here is apple. Okay, apple means some flow picture. Okay. Okay. The fluid mechanics can teach by using this book. It will be much easier. No mathematics. Okay. So this is the flow over cylinder, as you can see. This is experimental data, right? Flow cylinder is here. And once you have a flow, and we have a flow over cylinder with a It's one kind of shear flow, as you can see here. Okay, this is cylinder, and then once you flow field like this, you will generate a velocity profile like this. So you have a shear layer here, you have a shear layer here. Okay, and these two shear layers will interact with each other, so to generate like this, become counter-rotated. We call it vortex shading. Okay, counter vortex shading. Okay. And then one thing I would like to show you is a liquid jet. Liquid jet. Okay. Liquid jet. Not here, not here, not here. This is also the instability, one kind of instability problem. Okay. As you can see here, this is one instability problem in hydrodynamic instability. You have a two rotational boundary, and then at a certain speed, you will generate this kind of unsteadiness flow structure. Okay. So here we have this. This is one kind of instability. Okay. And here is another instability process. What's this? You have a fuel injection, right? 如果说你有喷油嘴 once you have fuel injection, okay, is anyone from the Professor Wang Juequan student here? No? Okay, well, the one professor in our department is doing the spray, right? Droplet spray. So you have the high-speed droplet, okay, impinging from a small fuel nozzle. Without any control, as you can see, without any control, look like this. Okay, without any control means if you eject the liquid, the high-speed liquid here, and outside the creation air, right? 外面的是空气静止的，very high-speed jet, liquid jet, and we have an interface here. We may happen, okay, the droplet happen here, okay. That we need this droplet, right? We need to tail down all this liquid current into liquid droplet, because liquid droplet can burn more efficiently. 我们需要抑低，不需要抑注，抑低能够烧得更有效率一点。Okay, and how to control? For this physical problem, you also can analyze by using the material in the chapter 6. Okay. We can find out what the fundamental frequency for this. Okay, that's the fundamental frequency based on velocity here. There's one precise frequency, okay, for governed by this physical problem. Once we perturb, okay, by into a small perturbation, like using the Piero, 用一个压电材料, okay, perturb inside this nozzle chamber. And small pressure will generate inside this pressure chamber. Once you perturb at right frequency, okay, you will kind of change to this. From here, okay, you change to this. Once you perturb at right frequency, okay. So as you can see, at the beginning, our droplet already formed very good interface modulation, and then break up into droplet. Okay, and each droplet is more precise. Okay, that's also the hydrodynamic stability. You can control it. So the difference between these three pictures, as you can see here. Okay, we introduce a different forcing here. The wavelength is different, right? This is wavelength. This is wavelength. So once I input this wavelength, 4.6 of diameter of this wavelength, I can force my liquid jet into this form. Very coherent. Okay, very beautiful. You can fix actually. You can fix. Okay. The location. Okay. And what else we have here? we did that in very old time, but I don't think I have here. Let's see what I have here. No. Okay, I don't think I have here. Okay, I think I will kind of 5 minutes left. Okay, now we'll complete our story here. Okay, so chapter 6 will be eventually going a lot of application. Okay, a lot of your research maybe in the fluid mechanics will based on chapter 6 concept. Okay, recently I read a paper. Okay, just yesterday I read a paper. It's talking about how to drop it on the surface. Okay, drop it on the surface. You drop it on the surface. Okay, and then you put a perturbation for it on the drop it, and to see how the drop it deform. Okay, the drop it will deform. Using a hydrolyzed speed analysis. Okay, as you can see here, how to write the Gaussian equation for this, you already know. Partially because there is a boundary here, so we have a potential flow here. Okay, and since inside this layer here, very important, the boundary here. So we may have to modify the boundary condition according to this viscous layer here. So this is more difficult a little bit. You deal up with that, it's already involved with the flow impinging on the wall, right? Remember this physical problem? If a flow impinging on the wall, we have a corner flow. This is corner flow. It's a potential flow. And this potential flow is also one of the solutions for the Navier-Stokes equation, because however the boundary condition didn't satisfy. So we have to modify here, right? And the flow field near here by a change of potential flow. They do a similar thing. The concept is the same. You can see even this is very complicated. Okay, it's published in the year of the year of 2010. Okay, by Korean guy. Okay, Ch6. Okay, it's a very famous university in Korea. Ch6 钢铁厂. Okay, so as you can see, what's the boundary condition here? What's the boundary condition here? The same dynamic boundary condition. Okay, we're using dynamic boundary condition. We have this physical problem, right? They have this physical problem. Okay, very similar. So you have to kind of, once you read the paper, you have to kind of reach, okay, and get an idea. Okay, even they are very complicated. A lot of mathematics. Instead of using a sine cosine function here, they're using Legendre polynomial. What? Do you know the Legendre polynomial? The one kind of a series of expansion. It's also normal mode. It's a polynomial, but it's very similar to the sine cosine, but it's Legendre, right? Legendre polynomial. Okay, and this polynomial also can be presented as like a sine cosine function, and then using Legendre polynomial as a normal mode, very similar to sine cosine function. Because this is so complicated, not the sine cosine function can represent the interface here. You have a wave traveling here, right? You have all kinds of waves traveling here. Whatever. Okay. Instead of using sine cosine function, that's ideally very similar. Dynamic boundary condition on the wall, and try to solve the equation, the Gaussian equation. Okay, and find out what's all these polynomials should be. Okay, I think like me, I'm still learning this. Okay, it's not too much surprise. Okay, why you know the concept? And you have to what? You have to able to apply it. Otherwise, all the lectures here is make no difference to you. You have to know how to apply it. Okay, you learn too much already. As a graduate student, you learn too much already, but you never have a chance to apply your knowledge to the real case. Try to think more. Okay, about this is all basic, very basic theory, basic concept, and how can they apply in the physical problem you have. That's really difficult. Okay, that's really you learn it correctly. Okay, otherwise all the knowledge for you is make no use at all. That's it. Okay, I think I will give you my comment here. Okay, apply it. Try to use your knowledge you learn in your thesis, in your research. Don't say this is a lecture. This is my research. It's totally. It should be connected. Okay. Okay. God bless you. Next week we may have a homework. Return to you and discussion maybe. Okay. So we will see you next week. That's the final week. Okay. If you want, okay.